Okay, so it's 9:30, so welcome to second day of the workshop. And hope you've all seen the programme, that we have an hour first on the RAMP new modelling initiatives, which Graham Ackland will introduce and share with a number of other participants in that. So that's for the next hour. And that will be followed by Peter Challoner from Exeter on uncertainty quantification. Then have 15 minutes break to make yourself a cup of coffee or anything else. And then we'll have Stephen Riley on socio-spatial networks. And then that should leave about 3/4 of an hour for final discussion. And the intention there is to discuss the various different approaches we will have heard about during the morning. And we'll have some breakout groups and followed by general discussion. So with that introduction to the morning, I'll hand you over to Graham to manage the first hour.
Does that look better?
Yes.
Okay, sorry about the initiative which the Royal Society has launched. The purpose of this initiative is to provide rapid assistance to modelling the pandemic, as the name implies. And this is the steering committee that was set up, led by Mike Cates, myself, Mike Batty, Chris Bishop, Peter Bruce, Julia Gogg, Kath Noakes, so the steering committee on RAMP. What I'm going to do first of all is explain how RAMP came about, how it happened, what happened next, and what we think we should be doing. So the first question that you might ask is, who the hell are you? So I'm Graham Ackland. I'm not an epidemiologist. I'm not an FRS. So why would anybody want me to lead a Royal Society initiative in epidemiology? Well, I'm not sure myself, but if I say a little bit about myself, it might help you to gather why. So I've been professor of computer simulation in Edinburgh for almost 20 years. I work in lots of different areas. So my career has basically been going into an area that I don't know very much about and trying to get involved, find out what's going on, and hopefully bring some new insights into what's happening. I've done a lot of projects with EPCC, which is the Edinburgh Data Compute Centre. And so EPCC are able to offer the technical support for RAMP, both in terms of managing the spreadsheets and the forums that you'll hear about later on. In principle, we can offer a lot of computing resource. That doesn't seem to have been a problem. I've also never stopped teaching, so I guess and therefore pitch in and talk about stuff that I may or may not know at a variety of different levels of expertise. So that's me. My first observation, a little bit about me, is things that I've worked on. Now, don't worry about the specific details here, but something I found interesting first coming into the area is how various areas of science evolve. So currently I work on a thing called density functional theory. Doesn't matter what that is, it's some kind of quantum mechanical calculation. The theory of it was invented in the 60s. It's really quite complicated. In the 1980s, a bunch of single groups wrote their own codes, and there was a winnowing down of codes in density functional theory. And in the 90s, there were a bunch of small user groups. Then people tried to parallelize the codes, and everybody's code became unmaintainable. And then in about the 2000s, we started doing proper software engineering. A small number of codes appeared, and now there are community codes in that area. Molecular dynamics, which is a way of simulating lots of atoms moving around, interacting with one another. The general idea of this was invented in the 40s, some sort of 20 years before density functional theory. It's rather simple. You're just solving with Newton's equations, and it has many peripherals. And up to the 90s now, so there were single group codes, and it went through exactly the same series of evolution as the density functional theory. But I think the interesting thing about this is that molecular dynamics, although the concepts are 20 years older, the arrival into properly software engineered code came 10 years later. And essentially that's because the central code is rather simple, and many groups can very quickly write a molecular dynamics code. You could do that in a week. A density functional theory code would probably take a couple of months. So it was interesting to come into epidemiology, a field that started actually by a blind Scotsman in the 1920s, William Kermack, and see where that field is. And it's probably not my place to lecture you on exactly where your field is, but I think it's interesting just to put this slide up and draw the parallels between these three areas, because I think the epidemiology community is somewhere behind, and you can understand for why, the software engineering route that the other things that I've worked in are. Okay, so that aside, that little introduction to me and why I'm interested, let me tell you first of all about what happened with RAMP. Mike Cates at some point decided to set this thing up, I think. Maybe the Royal Society decided to set it up. I got an email on March the 26th, do you want to be involved? By March the 28th, we sent out a call to all UK academics saying, if you're a modeler, if you're sitting at home, if you've got nothing to do, would you like to volunteer your time to come and work and assist groups that are working on the pandemic? By April the 3rd, so that's a week after I'd been contacted, we had a small army of 2,000 groups who'd volunteered to do this. We collected all the data in a big spreadsheet and then paused to think what to do next. The original idea had been to allocate volunteers to the research groups who are directly advising SPI-M, the government committee on pandemic influenza modelling. And so Julia Gog, who was in charge of that thing, went away, allocated about 24 people, I think, to work with the various SPI-M groups. And RAMP perhaps could have stopped there just 2 weeks after having started, having done a pretty useful service of getting the groups that really needed the resource up to speed. But then came the question of what do we do with the rest of the people? And then we realized the first mistake, or perhaps it was inevitable, that we'd made, which was that because of GDPR, we can't just put all the list of names on skills on the website and say these people will come and work for you for free, because we didn't have permission to do that. That has to go through the central committee. So RAMP task 1, led by Julia, the secondment of skilled people to existing SPI-M teams. We did it this way and what the advantages were. There's no funding. You can't come to RAMP and say, give us some money. There are no grant proposals. We don't assess whether you're any good or not. You don't have to write anything. Of course, if you come to us, we'll probably just cyber stalk you and see if we think you're any good. All the people were volunteers. This is obviously an indefensible way of organizing research funding, but in a crisis, it can be achieved very quickly. And as you see, within a week, we'd achieved, or Julia basically had achieved, the main original remit, the secondment of skilled people to existing SPI-M teams. About 1% of our volunteers had gone, and then the question came, what do we do next? So then we go on to task 2, and for people who remember the Hitchhiker's Guide to the Galaxy, there was this thing called the Golga-Frensham B arc, where basically a planet decided to send out into space all the people that it thought were useless but weren't really sure. And I felt that my task, RAMP 2, to do new models was a little bit like that. What do I do with this huge group of people? We don't know what to do with them. Hopefully we could do something a little bit more useful than just shoot them out into space. The flip side of the Golga-Frensham B arc is that the people who were left behind were all killed by a giant pandemic, which was kind of also interesting and germane to what's going on at the moment. So my first observation when I looked at this, look into literature, there are thousands of articles pouring out onto the various preprint servers. And so having been tasked with the idea, wouldn't it be great if we made some new models? My first observation was there's already no shortage of new models, and probably the last thing we want to do is to encourage everybody to go out there and make new models. So this is kind of weird that you stand up to do a thing, you look into the remit of what you've done, and you decide that it's a terrible thing. You don't want to do what you've been asked to do, and you think it's the wrong thing to do. So what do we want to do to make our new models useful, rather than this rather wonderful XKCD cartoon of there are 14 competing standards. I know, let's make one that unites them all. Result, there are 15 competing standards. That's the thing we're trying to avoid. But I think it is useful to make multiple codes, to bring together a critical mass of expertise and resources working on each, because what happened immediately, I think this is rather natural, when the epidemic broke out, everybody rushed off and wrote their own SIR code. Then they put in the thing which aligned most closely with their political orientation as an additional resource to it, and then stuck it on the archive, and everybody ignored them. So we wanted to avoid that. But I think it is useful to come at modeling these things from very different starting points, because there's an almost unquantifiable uncertainty in model design, which can be resolved a little bit by having completely different models that avoid any danger of groupthink or everybody doing the same thing and therefore getting the same answers. We were very keen that everything should be open source, because the second thing that everybody did, having written their own SIR code and knowing what was going on, was to say, oh, I'll go and run the big major codes and see if I can reproduce the results, and nothing was available to them. So they all went back and started writing even more SIR codes and clogging up the preprint servers even more, and that also served very little point. So I think it's really important that that codes are open sourcing, and anything that we were going to support in RAMP had to be open source. That was basically a requirement for our support. And documented access to data. I think we didn't realize at the time quite how difficult that would be. So the main idea was, when you set up an initiative, it's always tempting to do the most important thing, but we didn't want to do the most important thing because a lot of the most important thing was already happening. We wanted to look at things that weren't happening properly and do those instead. For example, to encourage people to provide resources for the people who are already charging on making models. We wanted to do reviews because this tsunami of papers that was appearing were all on preprint servers. Some of them were probably good, some of them were probably terrible. There was really no way of doing it, and to assist with code development. And we wanted to somehow amplify the signal and reduce the noise. So anything else wasn't being done could be useful to us. So the first thing was to instigate a mechanism for doing a rapid review, guided by SPI-M, who are the advisors to SAGE, who are the advisors to COBRA. So that makes RAMP kind of division 4 of the fight against of COVID, because we're filtering up through all of these groups. So one thing we wanted to do was that the people who are on SPI-M, who basically were completely swamped by the amount of work that was coming down at them, could cascade stuff down to us saying, here's paper, review it, let us know. We also wanted to push things upwards. So we instigated a crowdsourced rapid review, which is like TripAdvisor. Basically, Jamie will present this later on, but the idea is that our big army of volunteers can go look at the literature and push to our attention papers that they think are important. If many people think a paper is important, we'll push it on further up the chain towards SPI-M. So the idea is that the review process is going in both directions. We also wanted, having decided that there were some groups that we needed, that existed and needed to support, some new groups that we wanted to start, to enable people to self-assemble into making their own model efforts. So this is the kind of Tinder approach of creating, again, Jamie will talk about this, creating a way of members of the RAMP volunteer community finding one another in order to combine their skills and do whatever they want. We also wanted to provide assistance for, how to put it, the stuff that proper scientists don't like to do, the kind of tedious open sourcing and commenting and documenting, and actually what's called red teaming of codes, which is where you send a team in to try and break the code. So we supported that as an initiative. And the other things that, you know, groups, everybody knows you should do these things, but life's too short, and often we don't have the time to test things like parameter sensitivity, reproducibility of the main codes. So that we felt was a series of things that we could use this big army of people to usefully do. One of the things that coming in from the outside is that although you know nothing, you can see things which appear to be confusing. So I just run through how it appeared to me as a somewhat literate but not expert epidemiologist, you know, what was going on with things that actually came out in the press and in publicity. So the first thing that really came out when the lockdown started was 500,000 people are going to die, we have to lock everybody up. And actually that's really not very surprising. We had a disease that has a 1% death rate, and we have a population of 50 million people, so 500,000 people are going to die. And yet that somehow seemed to come as a big shock to the policymakers. And I think it's important to realize information we as a community need to push up, that will still come as a shock. And as a consequence of that, there was a big effort to care about the deaths that would come from COVID, and that's perfectly reasonable and understandable, I guess. The next story that came was that exponentials grow really quickly. And this again seemed to be a big discovery by the community, by the country, that if you have exponential growth, it very quickly grows. And the concern here was suddenly no longer that hundreds of thousands of people will die, but we will overwhelm the NHS capacity. The narrative has now moved on, and I think this is really interesting and something that perhaps we should have anticipated before, to this number R. So you probably don't want me to tell you what R is, but I'm going to tell you what it is in my opinion. So about R is that if you have R less than 1, then the epidemic shrinks, and if you have R greater than 1, then it grows. And that's a target which can realistically be explained to the country, and has been, and it's also a target that's achievable. If you care about R, you say the target is to get R below 1, and it can be done. If you care about deaths, then what's the target? The target, everybody will tell you, is we can have no deaths. And so it's impossible for the government or policymakers to sensibly try to sell any target that's about deaths. And so I think something that perhaps we might have realized early on is that R provides a target that the politicians can realistically hit. And perhaps we could have been a little bit sharper in promoting that as our message early on. This is drifting a little bit into the territory of SPI-B, but there we go. But anyway, none of these things are particularly difficult. You know, this you can probably do with primary school maths. This is sort of secondary school maths, and maybe you need to do an introduction to to epidemiology, like look it up on Wikipedia to understand about R. And none of it seems very difficult, and most of it is intuitive, but there were some very strange things. So here's a table from the Ferguson Model Imperial College Report 9, which I've only really now understood. So if you look across here, this is the total death rate as you increase the number of interventions, and actually it's the reduction in it. And so things get better and better and better as you put on more and more interventions. That kind of seems it seems obvious. Then the last step, which is basically from home isolation plus household quarantine plus social distancing, and then adding closing the schools, the death rate goes up. And so in that report, they're saying if you close the schools, then you kill people. And that never got presented anywhere in the literature, anywhere where the people were saying we're following the science. What on earth is going on? It's actually quite hard to even understand how that can come out of a model. What I think is going on is that when you close the schools, the children who previously were passing the disease among themselves and not dying, because children don't die, were then passing it into the community as a whole, in particular then infecting people who were at much higher risk of death. And so that's why the model produced this. But they went ahead and closed the schools anyway. So clearly, even at that stage, even though they were saying they were guided by science, they were basically ignoring what was said in the paper. Unless you believe that they didn't really care about deaths so much, because deaths are going down here. What they really cared about was the number of peak beds, which continues to improve with this additional intervention. So that was interesting and kind of confusing from the outside. And again, you know, there is a huge model behind this. It's interesting to me to understand why that played out the way it did. VAMP then caused a little bit of trouble with the report on Ferguson's code. So this graph here on the left got some traction on social media for a while. This is two runs which should be identical, because you should have run with the same set of random numbers because of the difficulty of initiating the random number seed in a parallel code. There was a little mistake that meant that you had a different set of random numbers. And these graphs actually, initially they tell you something very interesting. First of all, you always get the same result. The epidemic kind of goes along, explodes, and it goes across. But depending on what random number you have, the exact time at which that happens on a timescale of maybe a week is completely unpredictable. And that message never really got across. But what happened was, first of all, the message became, oh, the code is full of bugs. You know, it was secret, now it's released, it's got this bug in it. And then the ability of people with sufficient knowledge to understand and intent to cherry pick where the code is wrong. So if you and I look at this code, we'll go, oh, it goes along a bit, then it shoots up, and then it flattens off, and it's hard to tell where it flattens off, and that's where it shoots up, and that is what we would all understand should be happening. But the cherry picking interpretation is, well, what's the difference between this line and this line? At a particular time, you can find a place where there's a very, very big difference in the number of deaths, and then some sniffy comment, apparently a difference of 80,000 deaths is a small non-determinism. This is the kind of malicious misrepresentation that we're up against, and we have to be very careful about that. So that's a little aside. What specific projects have we supported? So just quietly to wrap up now, because I'm from Scotland, I was quite keen to support the Scottish team. So the Scottish COVID-19 Response Consortium were very keen to absorb volunteers. This was 7 different codes, 5 different groups working on it, basically coming out of the animal disease modelling area. And they've absorbed about 100 of our volunteers. Pyros is a code base, but we'll be hearing about shortly, developed by Ronnie Joy's team in Cambridge. It's a compartment model, basically an SIR model, now being extended to include social data, geographical data, and Bayesian inference. And I think this was one that we wanted to support because it seemed like a gap in the UK modelling market. The Ferguson code, which is an individual-based model, was now available online. There wasn't a code that people could go in and work on, working on compartment models that was of this similar level of usability. So this was kind of the code that we got behind. And then the RAMP forums, which is a mechanism for community review. So to tell you a little bit more about this, I'm going to pass over to my colleague Jamie Wood in York, who's been running that for us. So if I can work out how to turn my screen off, I'll pass you on to Jamie.
Okay, so as Graham has introduced it, I'm going to just give you a brief introduction to the RAMP forum and hopefully give you a little demo. So I'm a terrible interloper into this in that I've been asked to help along with my colleague John Pitchford to moderate. So I'm purely the representative there. I absolutely haven't done any hard work here at all, but hopefully I can introduce you to the forum and what it's for and how to get involved. Okay, so first and most importantly is why. So Graham has already alluded to this and even used the tsunami expression. And I've taken this from the paper that appeared in Science just last week. And there's an interesting statistic in there, which, as they put it, if the pandemic of papers on COVID-19 continued, we'd have something like 50 million papers on COVID-19 by the end of the year. And this is a huge problem because what we really need is to understand the key messages that we can find from the science and filter that up to the appropriate channels so that we can act on it. So it is an issue that we need to address as a community in order to be able to extract the right kind of information. So what's been set up is a Discourse server at the University of Edinburgh. It's mounted at the Compute Centre that Graham has already discussed. So a Discourse server is, again, like Graham has already said, is a kind of like a TripAdvisor type server where it enables people to post topics and then to be able to rate those topics. So we can use this in this context where the topics are new papers or preprints or reports that are coming out, and the whole community then is able to comment on those papers and hopefully those ratings that they give them we can filter back up to be able to see which papers are important, or even we can see what fragments of some papers which have really key messages that can be filtered up to the people make policy decisions. So let me give you a brief overview before I go back to the forum itself of how this process is hopefully going to work. So this is my horrendously complicated network sketch diagram of this process. So what I've indicated here is the papers arriving as in the form of the tsunami, which is taken from that Science paper, into the cloud, if you like, which is represented on the right. And what we have are two fora, one for urgent review and one for community review. The idea is that the community review is where anybody in the UK academic and beyond sector can pick up a paper, read it, post that paper onto this fora and give it a rating. And this provides an enormous, effectively, database of resource, which we can then filter upwards through the process to be able to see whether the insights are valuable on this paper. So the existing mechanism that's been set up is the Rapid Review Group, which is a small number of academics based in Oxford who are feeding directly into SPI-M and into the RAMP steering group. So this effort, this crowdsourcing effort, is designed to supplement the activities of that group in Oxford. So the idea is that this community review, if papers are important, then they can be moved downwards to the Rapid Review Group. They can be then given an extra review, and then they can be fed upwards via the to the RAMP steering group or to SPI-M directly, or however that needs to be processed. So that's the basic process, but we can add extra things onto this. And in particular, we can add an urgent review section. We have indeed entered an urgent review section where really key papers are coming out that the group in Oxford want to have a more a balanced look at in a rapid fashion. And we've had a number of these papers come up already on the forum where basically they can be put into this urgent review section and people can very rapidly give them a rating, and then they can be fed on upwards in a more timely fashion. And in particular, we can move between this urgent section and the community section as needs be. So if a paper is seen to be particularly important, is picked up by somebody who wants to be fed up more rapidly, it can be shifted into the urgent review section, and vice versa, where what a paper that was previously believed to be urgent is deemed to be less urgent, it can then be pushed back down to the community review, where more eyes can look at it, and perhaps on a longer time scale that can eventually be fed up. So that provides a mechanism where papers effectively can come from the cloud of reviewing expertise, which is vast because of the number of respondees we have to the RAMP effort, and eventually find their way up into the food chain that Graham has previously described. Of course, given this, we have this forum, we can also use it in other ways too. So one that I've illustrated here is the idea that we can use policy questions to bias the movement of our community to review the kind of papers that SPI-M and SAGE need answers to. So I've indicated this here with the policy questions on the right of the slide. And so policy questions can be fed, if you like, down from SPI-M and SAGE and the RAMP steering group, and then they can direct the efforts of the community review, and then hopefully that will work as a virtuous circle where the kind of papers that people are looking at are biased towards the kind of questions that are needed to be answered. So that's essentially the overview of the process of the community review. So I want to just briefly talk about the forum itself and where we've got to. So as I said, I'm a slight interloper in here. I was asked, along with my colleague John Pitchford, to lead a moderation team for this new venture. I've not been involved in the back end of this at all. We have an excellent colleague up in Edinburgh, Chris Ness, who has basically built this server. It's an all open source server, and he's been invaluable in getting small changes done at a very short notice so that we can make it behave as we want it to behave. And so you can see here the areas of the outputs, as I've indicated on the flow and the flow chart. In addition, we can also provide services where we can try to basically matchmake people, where we can allocate modelers by putting out appeals to the community for particular skills and try to move them either to the RAMP teams or to other people's ventures to the creative modeling. So this is a way of trying to harness this huge number of people who volunteered for the RAMP effort. I'm going to briefly, hopefully this won't go wrong, is to show you some of the way in which this process works in practice by showing you some examples of papers last week. So I'm going to try this quickly. So here's an example of a paper that was posted, you can see here, by one of our moderators as it happens last week. And this addresses an urgent question about the masking on COVID-19. And what you can see is we received a series of reviews of this over a period of time. I'm going to try and not reveal too much about the people, but this is all on public server. But essentially, it enabled people to read this paper in more detail to see whether it was a valuable paper to be fed upwards to the chain. So we can see what we have is a proper discussion going on here, that people disagreed with some of the reviews and then agreed. And ultimately, the paper filtered through and it was given a 2-star rating. Or a 2.5 star approximately. And the key thing here is that nobody is in any way questioning the academic quality of the paper, but we're suggesting that this paper is not providing the kind of urgent UK impact that it perhaps would like, and therefore we are suggesting it isn't of the, it needs to be fed upwards towards the RRG and onwards to SPI-M and SAGE. By contrast, I'm going to show you a different paper which came out in Science last week, rather predictably that it was more important. So in fact, it was me that posted this to the community review section, and very rapidly this paper received a number of very positive reviews, 4- and 5-star reviews. it was shifted to the urgent section, and was within days, it was pushed on upwards to RRG and onwards up the chain. So you can see here that we have a mechanism for flagging these to RRG. And once it had been pushed into the urgent section, you can see that it was then actually pushed back for community review. And the value here is that then that's a suggestion to people that although the main messages of the paper have been pushed upwards, any further reading to find extra details, in particular, this particular paper had a lot of data in its supplementary information that potentially valuable extra insights could have been drawn from. And that in the community review section, that gives time for that to happen. So that's the overview of this. So the last thing to say is, when is this happening? Well, the simple answer to that is now. We need to get people, more and more members and more people on it to generate more reviews as soon as possible. I've put the web address here, and it's on a number of the other slides as well. We are accepting members by approval, but we're keeping an open mind for that. We have a very diverse community that are on the RAMP responders list. So we just encourage people to sign up really and get involved with this effort. And finally, I have an acknowledgement slide as much as I can. So it was Mike Cates and Graham who asked John and I to coordinate this. Chris Ness and Kostas Kavadasakis at Edinburgh have been invaluable in providing the support for us, both on the technical and on the more practical sides. And we were able to recruit a diverse team of moderators from a number of academic institutions to help out and get this set up. And I'd like to thank my colleague, John Pitcher, I think he's also on this call. Okay, thank you.
Okay, thank you, Graham. So my name is Ronjay Adhikari. Let me see if I can start by sharing my screen. Is my screen visible?
Yes, that's fine.
Yes.
Yeah, okay, very good. Okay, so I want to say a few words about the Pyros library that we have built over the last 6 weeks. You see mentioned here. I'm the first name. Presenting with me together will be Liz Cucci and Julia Kapler. So what I want to do is I just want to give a sort of overview of what the library is and what the thinking behind the library is. Who am I? I'm a lecturer at the Department of Applied Mathematics and Theoretical Physics in Cambridge. I have impeccable credentials in epidemiology. I've published 2 papers in the last decade, one as recent as last month. So with that caveat, I want to sort of tell you a little bit about the Pyros code. Okay, so what are we trying to do here? What, as I said, since none of us are epidemiologists, we have tried the idea of hard coding models, but rather allow for a platform which will allow more or less arbitrary kinds of compartment models. Okay, so the idea here is that we want to follow this sort of modeling philosophy, that there is data, there's a model, you fit the parameters of the model to the data, you can use Bayesian inference to figure out whether that's a good fit or a bad fit, you use it to forecast without interventions, include the interventions, and then see what the new forecast is, compare with the data, hopefully. And if this is not matching with data, or you think that something has been left out, or you've got more data, you repeat this whole loop all over again. So you either gather more data or you build new models. Okay. So the important point is that the platform has 2 components. It has a data which is fed into it, and it has a model which there are predefined set of models and a sort of arbitrary model that the user can build. Okay, so in addition to all of the standard epidemiological compartment models, so I'll just make one sort of correction to what Graham said. It's not that we have only the SIR model. We have more or less the standard compartment models that one sees in epidemiology. So I've listed those ones there. We have SIR models, SIR models with 2 infectious classes. We have stages so that non-exponentially distributed residence times can be dealt with. And in addition, we have a generic language in which to define an arbitrary compartment model. So there's this sort of meta language, which is a JSON format, very easy to learn. And you just say what classes your model has, what the infection rates are, etc., and you can build up a completely general model using that. Now, what distinguishes this library is that once you define this model, either in terms of these predefined models or your user-defined model, you can do automatic inference on it. So there's an automatic way of doing inference, which uses Gaussian processes. And that tells you both what the parameters ought to be given data. It tells you how well the model actually matches data. And you can sort of compare different models and find out which of these models are best likely to fit data. So just a very quick example of this kind of thinking. So this is the figure that I'm going to show you here is a comparison between the Ferguson model. So we ran the Ferguson model. So that's the dotted line in this curve, and it's called COVID-SIM, with a standard set of parameters. And we pretended that that is epidemiological data, okay? We then use the first 20 days of that simulation to fit a SIR model with 5 stages. So the 5 stages was there for to take into account the non-exponential residence time distribution. And we fit it for the first 20 days, and then we forward predict it. And you can see that from this point onwards, this is just a prediction of the model, of the model that we have fitted. And it agrees reasonably well with the Ferguson model. So the idea here is that if you have this complex epidemiological model who's, with lots of parameters, and that's supposed to mimic real life, you can actually use these compartment models to sort of capture with a far fewer number of parameters essentially what's going on. Of course, you might ask, well, what about the interventions? We're working on the interventions. We have results, but it's not at a stage that I can show you with confidence today. But we can also do similar things. We can use COVID-SIM with interventions, learn how much the interventions are suppressing contacts, and then forward predict from that point onwards. Okay, so this is essentially the philosophy. How do we, just one more remark about what the structure of the model is. So instead of having individuals, we have metapopulations, and these metapopulations are segregated by age. There are contact structures between, so the rates of contact between different age groups, and that is really the key ingredient that goes into the model. And this is an example, for instance, of the kind of contact structures, and these contact structures can vary from the sphere of contact, so the different kinds of contacts in the home, different kinds of contacts at work, school, and so on, and of course there's the age distribution of the population. So these are the sort of inputs that go into the model, and the intervention is modeled by changing the nature of these contacts. Okay, so we have all of that machinery built in, and as I said, we can allow for arbitrary epidemiological models simply because we want to allow for a platform rather than input our own expert knowledge, of which there is very little. Okay, so with those sort of general sort of overview, I think I'm going to hand this over to Julian, who will show you how this model works, and for one example, and then to Lucas, who will show you how we can extend this kind of model to spatial, to resolve sort of spatial epidemiological phenomena, and he'll show you a simulation of an epidemic in London. Okay, so can I ask Julian to come in, please?
So the example I will present is, so our code is on GitHub, and the example is there as well. I will show it to you now, but I'm also posting the link, but maybe you better follow my, what I'm showing. So then, so this is Jupyter Notebook. So all our code is based on Python. And in this notebook, I will just show you a simple example for a control protocol. So what we do is we have an initial lockdown that is then partly released. And we simulate this numerically with a stochastic model, which I will explain in a moment. And as Ronojoy said, so we are working on doing inference on actual parameters, but for this model example, we take parameters that we deemed reasonable. But what we use is we use the actual age structure of Denmark and the actual contact matrix of Denmark. So you see how these how this contact structure works in practice. And so the model we consider is called by us the SEAI5R model. It's a compartment model, as Ronojoy said. And it's, it doesn't contain space yet. It's just compartments. Lucas will talk about spatial models. And so in this model, you have susceptibles. These are people that can get sick. And once they are infected, they first become exposed where they don't show symptoms and are also not infectious. and then they go on to be activated. Here they still have no symptoms, but they are infectious already. And it's not clear whether they will be symptomatic later or asymptomatic. And then they either become asymptomatic and recover, or they become symptomatic and then they can recover, or they get a worse condition and have to go to the hospital, from where they can again recover, or get worse and have to go to the ICU. And in this model, they can again either recover or they die. So it's just one of the models that are implemented. And I mean, there's a lot of models in the package, and this is just one of them. Okay, so this is the model. And for each of these classes, we have age structures. And we use the Denmark age structure that consists of age brackets of 5. So you have, for the susceptible, you have those that are between 0 and 4, 5 to 9, up to 75 to 79 years. And okay, so we have 16 age classes for each of these stages. And these interact with each other via these contact matrices that we also have for Denmark. Ronojoy showed you a picture already, and there are 4 spheres. So you have the home contacts, you have the work contacts, you have the contacts at school, and you have the remaining social contacts. And you can see already it makes sense. So if you are at work, you interact with people in the middle age classes, because this is kind of the working force, and at school mostly young people interact with each other. So this is kind of, I mean, these contact matrices, they make sense. And then for our model, we take parameters that we deemed reasonable, but that are not fitted to real data. And for the protocol, we consider, what we do is initially nothing, there are no restrictions or anything. And so the contact matrices, the total contracts are just the sum of these contact matrices. So you have contacts in all these 4 spheres. Then after 20 days, we start a lockdown. And this means that you only have the home contacts plus 10% of the work contacts. And we make a short transition period where you have 40% of the other contacts. So schools are already closed, but people still like socialize with others. And this starts after 20 days in our simulation. And then after 5 more days, people start taking the lockdown seriously. And the contact matrix becomes just home plus 10% work. And then after 45 more days, we add schools. So after 70 days of simulation, we change the contact matrix to home plus 10% work plus 50% of schools, which means that the schools open, but now with social distancing, so there are more contacts at school as compared to before the pandemic. And so this is a control protocol that you can implement in our model. And yeah. And the contact matrices, they are provided by the program. So you can just load them once you download the program. And then what we do is we take this protocol and we simulate with Pyros, and we do stochastic simulations. There are also deterministic simulations, but here we use stochastic ones. And because it's here you see a single trajectory. This is the time of the simulation in days. This is the number of active cases, which are those that are symptomatic in the hospital or in the ICU. And here you see, here's where the lockdown starts, here's where the schools are reopened, and you see a stochastic trajectory. Once the lockdown starts, it goes down again, and once the schools are open, it goes up again. And because it's stochastic, of course, you have to do averaging. So here we do 150 simulations, and you see they are a bit different, but qualitatively they're all the same. And with such an ensemble forecast, of course, you can do like some analysis. You can ask, okay, how long does it take after the initial lockdown until you reach the maximum in the number of active cases? Or once you release the lockdown in the schools, how long does it take until you reach the minimum here? And then you can simply do some statistics on these things. And here we did this. Here we plotted, for example, the time from the beginning of the lockdown, which was the red vertical line in the previous plot, until the subsequent peak. And you see it's rather sharply peaked around 16 days. And the time from the opening of the schools until the minimum is not as sharply peaked. It's between like 2 days and 25 days, and the mean is 10.7. And so this is kind of a thing you can do with our CAP package. And once you, so here now we have the stochasticity of the model, but once we have the Bayesian inference, for example, on this Denmark data, There's also the model parameter uncertainty, which can also be folded in the forecast. And then you have more variation typically because you not only have the stochasticity of the model, but also the stochasticity of the parameters. And just as a final point, one interesting thing in this example, we think, is that once you open the schools again, even though you have only 50% of the contexts, the R is so large that the curve starts increasing again. And if you change the protocol a bit and you say, okay, we want only 20% of the school contacts as opposed to 50, then you can do the whole analysis again. And you will find that then if you have more stringent social distancing at school, then the curve does not increase again. So this is kind of interesting, small, more or less toy example to show you the capability of the PYROS framework. Yes, and that's basically what I wanted to present quickly. Yes. I don't know, I think questions will come after the
yes, so thank you, Julian. We should probably wrap up now. So I guess Dennis can handle the queries. Ooh.
My screen. Right. Okay. Well, thanks very much for that. So we have a few minutes for a couple of questions. If anyone would like to ask one, put up a hand or mention on the chat. Anyone got a question?
Dennis?
Hi.
Yes.
Oh, somebody else. I thought I heard somebody else. This is Deirdre. Did somebody else say something?
Go on,
No?
Deirdre, you first.
Oh, okay. This is Deirdre Hollingsworth from the University of Oxford. I'm an infectious disease modeller. Thank you very much. And we're really impressed by everything that RAMP have been doing. And I thought it was, it was a nice presentation of some of the stuff that you're trying to do in sort of standardizing and improving code and things. I think one of the challenges, I think, for us with RAMP is, there's a little bit of reinventing the wheel going on, like, stochastic events in the start of an epidemic obviously determine the timing of the peak, or, with an R03, like 50% reduction in contacts doesn't control the epidemic. So how do we work better with the people who are in RAMP, who are sort of recoding models and slightly reinventing the wheel, so that we really maximize the utility of these efforts, is my question.
I think the answer is to tell us what you want. Most of us are and recognize that we are not experts in this field. If we are let's say rediscovering the wheel, that's at least somewhat encouraging that we haven't discovered something that's completely different. But the idea is establish groups to do things that previously you may not have had time to do, the kind of beautification of the code, the testing of parameters and scenarios, just the extra manpower that we can give you now that previously you might not have had available.
Yeah, I think that's really great, and I think the direct RAMP volunteers have been doing that. I guess I'm thinking, what can this program offer you? I guess is more where I'm focused, I think. Sorry that I didn't really focus my question in that way. So, one of the things we've discussed is to offer training modules. So we try and sort of have people either point you to classic epidemiological lectures, or provide you with, like, if you have questions about contact tracing, talk with you about that, or, or are these kind of workshops where we give seminars and you sort of learn about the field, but we're not really doing work in anger per se? What, just from the group of you, what kind of things would you like to come out of these interactions?
Well, the thing with Ronajoy's code is that we observe that if you ask the question, I'd like to do some modeling in some small neighborhood, some local area, some different country where the existing groups don't have time to do it, where's the framework I can go for a compartmental model, build it quickly, put my local neighborhood in it and run it? And that didn't exist. It wasn't there on in any open source publicly available code that we could find. And that was the rationale behind Ronald Joy's model. With Joy's model, essentially it was the same thing. That there was the Imperial code that was not public source. People who wanted to investigate things could not go and use it. And so it was one of our priorities to get that into a situation which it is now, that people could download it. It actually is now compiled across the UKRI computers.
I think that's really cool, and I think it's a fair criticism of our field that we have not, partly because I think we're perhaps not such strong programmers, we haven't been making our models as open source as we should have been, and I think that's spot on, and I think, you know, we appreciate the Office of Support in doing that. I think also there's not as much visibility of the number of modelling groups who are working, so there's quite a lot, and I hope this week is also giving people an impression of the number of modelling groups that are working, and they're not publicising what they're doing and making it public, as you're suggesting. So I'm, you know, because it seems like, you know, this is a really expert group that you have, and, you know, we need to tap into it in the right way. So I'm going to actually call on some of the people on the call, because there's like 57 participants. What ways, you know, what do you see exciting in this, and how can we tap into it? I'm gonna pick on people if they don't start volunteering to answer the question. So raise your hand, and Dennis will call on you.
Well, thanks. I mean, maybe we could come back to this during the session at the end of the morning, I hope. Just say quickly, I think there is some open source software, and it'd be interesting to compare Pyros with what's available, and more generally, it's with models like I understand the Imperial model as used by Neil Ferguson Co. is something that's been growing over a long time, and probably its code is not as easy to understand as it should be, and being able to sort of skin a model and look at what's actually in there, and anything that may be missing is of course the more people who come along and do it. So I think as I understand it, somewhere in your team there are people who like sort of taking other people's models to pieces, and I think some effort on that could be valuable for trying to establish what models we have and how we can improve them. But thanks very much for that. But
Dennis, a couple of people had their hands raised. Pavel Kravitsky and Steve Riley.
Yes. Okay, well, quickly, please, because I think we are running a bit over time. But I was trying to cover Pavel's point, which was that there are existing existing epidemic models. But Pavel, do you want to add to that?
Yeah, just very briefly, if you're looking for something, there is for example, something like the Epi Model project. I don't know what, I think I pasted the link into the chat. It's run by Sam Jeunesse, who is at Emory, and he, I think, is giving a talk either tomorrow or the day after in the workshop as well. So I think that you know, building on that might help, because it already provides a framework that is very extensible and well engineered, and could facilitate, well, could sort of be contributed to without reinventing the wheel. That's all I wanted to say.
Okay, thanks. And Stephen.
Yeah, thanks a lot. I just wanted to say that I agree very much about the open source and the engineering, and I think that we're a lot better on open source now, and within R, we're not too bad on engineering, but my sense is that the larger code bases, especially if they're old, and I'll give an example when I speak in a little bit, I totally agree that the level of software engineering is not great, and I really appreciate people coming in with the mindset that it can be improved and we can make much more valuable kind of code assets for everyone. So I just wanted to agree strongly.
I mean, I'm sure there are other questions, but I think I'm just conscious that we're running 5 minutes over time. So